So welcome everyone. Say hi in the chat. I'm going to launch a quiz soon to find out more about you. I'm Matt. I'm going to be hosting this webinar. I'm going to introduce our guests pretty soon. Feel free to let me know in the chat about audio or video quality problems. We had nearly 900 people register for this. Actually, I think it went over 900 in the end. So clearly a very popular topic. Normally I only get nervous when I'm doing live talks, but with 900 people registered, I feel nervous for this one. So I hope nothing goes wrong. I'm going to launch this poll because we want to find out a bit about you. So we really appreciate your feedback. Tell us about you. We're especially interested to know if you're interested in taking part in one of the upcoming shuttles. Let's see, where are we at? Normally we get like 50% of the people who register turn up, and everyone else emails me saying, can you send me the video? So we're up to about 260. So I'll start off with a bit of news. Welcome to the eFabulous Analog Layout webinar. We've got the big news is we've got the next Chip Ignite shuttle closing on April the 24th. So you've got a bit less than 2 weeks. And that's for 300 wafer level chip scale parts. Also, we've got Tiny Tape Out is closing. eFabulous is a sponsor of Tiny Tape Out, and that's running on the same shuttle, 2304C. Tiny Tape Out is a way of combining lots of small educational designs into one chip and makes it even cheaper. We're going for $100 price point, including a PCB. So if you're interested to know more about that, that's one of the options in the poll. Closing on April the 24th. And then the next Chip Ignite is closing June the 5th. That's for 100 QFN. A lot of people have been asking when is MPW9, the Google-sponsored free open source shuttle, and there's still no news on that. But I am pleased to announce that eFabulous is starting a free open source shuttle. So that's going to take up a bit of the slack on getting your designs taped out. And that's the first one is going to run on the 2306. So that's June the 5th. There's a lot of stuff to be decided. And we're thinking we're going to give away 4 slots on Chip Ignite. 2 will be full size and 2 will have 4 designs each. So there'll be 10 prizes. You'll submit a proposal first, like a 1-pager telling us about your design. And we're going to have like a minimum level of quality to enter the competition. So we don't know exactly what that's going to be yet, but it's going to be ticking off everything on a 10 or 20 point checklist. And then to decide who gets in, we'll have like a community can vote, but we'll also have a panel of judges yet to be appointed. And we're going to be trying to choose stuff that is going to make the biggest contribution to open source IP, especially reusable, useful stuff. So stay tuned for that. We'll be announcing that more on the mailing list and in the Slack channel. Now, this webinar is all going to be about doing analog layout for tape out. But I also just want to show you a tool that me and Uri have developed called SillyWiz. And this lets you, in the web browser, extremely simply draw and simulate, look at cross sections, do real-time changes of simulations, and run all this in the browser and see what the result is. So if you want to learn kind of the basics of how analog stuff actually works and draw simple circuits up to and including CMOS, then check out SillyWiz. There's lesson plans up here as well to take you through it. So moving on to what we're covering today. Don't worry, we will be recording. and sharing on YouTube later. That's the number one question. We'll be emailing you all the link. I recorded over 4 hours of material with Tim and Thomas, so we're not going to be playing all of that here. But I am going to be uploading the original recordings to the eFabulous YouTube channel. So go over there, subscribe, like, ring the bell. And this is based off the previous webinar that we did with Stefan Schippers. So in that webinar, Stefan showed us how to do schematic capture and simulation with XScheme. And that has been uploaded onto YouTube. So if you want to find out more about that, check it out there. The repository we'll be using is down here, this schematic here. And then we've got some recommendations from some analog crew, these books, this Analog Devices Handbook. Also, particularly like to recommend Bradley Minch's videos on YouTube. He's done a lot of good layout and analog stuff there. We'll be referring to Thomas Parry's Klayout GitHub repo, which is here. And then finally, we've got some open source ASIC resources on this GitHub page here, open to pull requests. Okay, so let's see what's going on in the chat. Good. Audio, video, 10 out of 10. Is this recording going to be available on YouTube? Yes, it will be. So without further ado, let's invite onto the stage Thomas Parry and Tim Edwards. How are you both doing?
Good.
Hello.
Cool. So Thomas, you're based in Rotterdam in the Netherlands. Can you tell us a little bit about your background and what you're working on at the moment?
Sure. So I'm a mixed signal design engineer, worked for a number of years professionally in a mixed signal design consultancy. And then when the open source Silicon movement started, I jumped into that head first, and we're in the first 2 open source MPW shuttles. And then now I'm also working on a new startup that's starting to use the new capabilities of open source and agile semiconductor design to design satellites the way they do design iPhones or MacBooks with their own custom silicon.
What's the name of your startup?
Spherical.
Nice one. Okay, and Tim Edwards, head of analog at eFabulous. Do you want to give us a bit about your background?
Yeah, well, my background in analog design goes back to grad school at Johns Hopkins, actually Stanford, and then Johns Hopkins. And my PhD thesis was in analog VLSI, some stuff similar to what Carver Mead did in the book that I was recommending, which may or may not still be in print. It's a 1989 book, which very much dates me. And after that, I worked for Johns Hopkins Applied Physics Lab doing space qualified analog layout. After that, I worked for a startup doing gigahertz range RF layout, and that got bought out by Analog Devices, which I did for a few years until I jumped ship and started working for eFabulous.
Thanks, Tim. Okay, we've got one person asking if we can turn up the volume, but it sounds fine to me. Let us know if we've got a lot of people saying that audio and video is 10 out of 10. So let us know. Sometimes it can just be settings on your local side. As you can see, the size of my microphone, but that doesn't mean I've got the gain set right. So yeah, let us know. Okay, so what we're going to do is we're going to start off with looking at the recording that I made with Tim. We do use Magic to do the layout of the comparator from last time's webinar. We're going to take a look at generating the transistors, then doing the layout, doing the extraction and the LVS. And then we're going to switch over to Thomas for the last part. And we're going to look at the same kind of process, but using Klayout. So we'll start off. Tim, I'm going to start playing this video, and we'll be skipping around through it. Like I said, it's kind of an hour and a half of recordings. We're only going to show like about 40 minutes of it here. So as we go through, please feel free to ask questions about stuff that you're interested in, and we'll try and cover all the questions. So let me share my screen again. Here's all my bookmarks. So we're going to start off here.
Okay. To here, and then I should be able to run xscheme on tb bandgap opamp.sch. There we go. All right, so I'm going to keep this around. Yeah, I think my audio just dropped out. The op amp, and this is the only one that I'm going to try to do the layout of. I believe that's what
Yeah,
you did with the
that's what I did
Klayout
with
as well. You just did this particular one.
Mhm.
Okay, so as I said, I'm going to keep this thing around. I'm going to make this window a little smaller so that I can see what I'm doing, but have most of the screen available for layout. And then I am going to, actually, let me leave that window up with xscheme and start a new window for Magic. Zoom in on that a little bit. So it's, there we go. That's the same size as the other one. Tutorial layout. And now I'm going to run Magic. What I've done, I don't like to type in the whole command line for Magic. So I have created an alias, which is something you can do in C Shell or Bash or whatever. You can create an alias from one command to another. So if I wanted to type out the whole thing every time, I would do like DOGL, which is my OpenGL. That's my favorite graphics to work with. The standard graphics are based on X11 and are not that great. The other option is Cairo graphics, which is very similar to OpenGL. And then the startup file is like xscheme. It comes from the PDK. So there's a RC file, and that comes from the same place. And user share PDK. Libs. In fact, I'm usually a better typist. I can't type and speak at the same time. Yeah, sky130a.magicrc. So that's what I would normally type. I've got a little alias called Magic Sky. So if I exit Magic and re-enter it at any time, I'm not going to bother to type all this, but that's the full command line there. All right, I have got Magic up now. I'm not sure I can make this command window any bigger than it already is. So unless there's, I don't think there's a view here. So you may have
to see a zoom when you popped out that menu somehow.
Wait, what? Really? Where? Maybe you want to skip ahead from here. I'm not sure that had to do with this, though. As far as I know, there isn't anything in TK that will zoom this window for me. But I'll tell you what commands I'm typing in.
Okay.
Actually, let me just try the usual. No, the usual keystrokes don't work on that. That's what I thought. Yeah, if you can't read anything on there, just let me know. And if I haven't mentioned it while talking, then well, I can see it on my monitor. Okay, so in order to do this, the first thing you'll want to do is get this schematic into some form of layout. Now, Magic does not make any pretensions about being able to do a full analog layout, but it can create devices, it can create sub-circuit hierarchy, and create pins. Now it's going to drop them all, sort of concatenate them into a row, and it's going to be a big mess and have DRC errors, and you have to then go and reorganize it and wire it up. But it's a starting point, and it's a lot better than starting completely from scratch. So along with when I did the command line with the RC file, that used a startup script that is on top of the tech file, so to speak. And that startup script does a number of things. And one of the important things it does is it runs a tickle script that has all of the device definitions for the parameterized devices in it. And it creates up here in the menu, these menu items, devices 1, devices 2. These are device generator scripts. So they are like what you would call P cells in other tools. I have no idea whether the term P cell is copyrighted or not, so I do not like to use that. I just call them parameterized cells. If I wanted to create an NMOS from scratch, I would go over to my devices menu, click on NMOS, and it would give me a pop-up window that allows me to type in for each device the width, the length, and there are a number of options that I have that I can select, and that tells me how to draw the device with a whole bunch of different possibilities, like how I want to contact it up to metal, or whether I want to have contacts on both sides of the gate or otherwise. Now, when I come from Xscheme, I'm going to have a net list, and that net list obviously doesn't say things like, do I have guard rings around my devices? Do I have contacts up to metal 1? It's just going to say I have a device and it's got this width and this length. So there's a loss of information that goes from layout to schematic, and consequently, if you go from schematic to layout, there is a certain amount of information that is added to all of these devices. And so there are defaults in the PDK that say for every device, if I import it from a schematic, it's going to get a certain number of default options like a guard ring around it and so forth. I can adjust those once they're in the layout. Obviously, if that information is not in the schematic, there's nothing I can do to get it into the layout before I do this transfer. So let's get started with that. The first thing I will need, I can't go directly from a schematic to a layout. I have to go from schematic to a netlist to a layout. So I go click on netlist. Before I click on netlist, I want to make sure I have pins on the top level. And that means that when I read it into Magic, Magic is going to want to see a subcircuit line. And there is an option in Xscheme down here called LVS netlist top level is a subcircuit. That's going to create the subcircuit line. So once I have selected that, I should be good to go to create the netlist. And all I do is click on it. If it didn't pop up a window with lots of error messages, then it was all successful. And it should be, by default, there is a home directory .xscheme/simulations where that thing should have appeared. And since this this itself, although it's inside a test bench, it is called 0opamp.sch, and that's the netlist it should create. So let me go over here. This is also something that is loaded by the PDK options from the startup script, which is it adds a menu item called File Import Spice. So that's the important one. So I'm going to click on Import Spice. Now I need to go find it. So I'm going to go back to my home directory where I should have then a .xscheme, which is right here, and simulations. And I should be able to find that. What did I say it was called? 0opamp. Yes, there it is, 0opamp.spice. So if all goes well, then I should be able to click on this, say open, and I'm going to get something. Boom. All right. Now it takes a few seconds. You saw it doing something. And if I view out from there, that is exactly the sort of mess that I said it was going to create. You see everywhere you see these.
What a time saver.
That was a huge time saver. Yes, if you imagine having to go through here and for each of these devices,
When we
going
did
up
this
and
with
selecting.
Klayout, it took us about an hour.
Yeah, so that is a huge time saver. Now it'd be an even better time saver if it would go wired up for you, but the process of figuring out placement and wiring of an analog circuit is at least the complexity of figuring out placement and layout in a digital circuit, and you know the size and complexity of the tools that do that. So that's not to say that there aren't such tools for analog, but they are very complicated, and to make one is a lifetime worth of research and effort. Needless to say, Magic hasn't gotten quite that far because I have plenty of other lesser areas of development to work on.
Yeah, I remember when I saw you doing this, Tim, I was like, whoa, this is amazing. Because we'd spent so long doing this with Klayout, doing each of the cells individually. So I'll show that bit later on. So I'm going to jump ahead now to starting the layout.
With the P devices up toward the top, the N devices toward the bottom, because all of our, not all, but most of our P devices are going to be connected to the power rail, top power rail, and the N devices are going to be connected to the ground rail. So that's the first thing I'm going to do is I'm going to find the key devices, which are the ones with the greenish outline. That is an in-well that's underneath them. So I've already got this selected with I for instance, and then I'm going to move my cursor somewhere and type M for move, and I can move that around. And let's just move these up top so I can see what's up. Okay. Nope. Oh, didn't mean to move that. Nope, wrong one. There we go. I'll cover myself and answer questions. Yes, I'm running this natively, not on Docker. Here's one. And yes, you can import directly from a SpiceNet list. You don't need a schematic. And move that up.
I can always mute you when you want to talk.
Oh, that's all right. Move that here and then separate these out so I can remove
with
all
lots
the
of pauses
DRC
anyway.
errors. Purple boxes on the left are pins. I'll get to those in a bit. And now that I've gotten some of these things out of the way, you can see over here on the side, there are all these pins. Now, these pins may not necessarily be a good size. I think I've made them a bit overly large, but I had to make some choice for how it imports pins because like devices, you lose information from layout going to schematic. So the schematic doesn't say anything about where the pin should be, what layer they should be on, or how big they should be. So Magic makes some guesses, and those you can either use them as is or move the pins to different layers. But at least you get all the pins that were in the schematic. So anything that had a little red arrow on it is marked as an input or output has been turned into a pin. And there should be, if
I could skip ahead because I get lost for a little bit there.
Text is in blue, they're considered ports. And that means Magic will treat them as port names for a subcircuit when it generates a subcircuit. Now I should be able to say like port use, default port.
No, totally wrong.
Actually, I think in this case, I might need to.
Yeah, remember this. We can skip ahead.
Yeah. Just skip ahead.
Let's move on to that interesting.
Yeah, somehow it didn't occur to me that you can only get port directions from a left file. You can't get that from a schematic.
Mm-hmm. Okay.
Obviously, the port direction is in the schematic, but you can't. That doesn't translate into the netlist since it's only reading from the netlist. It doesn't know what direction the ports are.
And we've got a question saying, "What's the difference between pins and ports in this context?"
None.
None. Good.
Except that in the schematic, you generally refer to them as pins, and I have a tendency to call them ports in Magic.
Okay. All right, so let's jump to here.
This is an analog layout. It's got differential pairs. What's most important for analog layouts is that when you have a differential pair, they are supposed to be well matched. So being well matched, there are lots of ways to make things well matched, and that usually involves dummy devices and so forth. And I'm not going to get that complicated with that because I'm just trying to do a fairly simple, quick layout here. But the one thing I can do at least is put those devices close together and have them sharing the same area of guard rings. So here, for instance, these are the PFETs. So M3 and M4. See, this is M20. All right, M3 and I see M3 and M20. Okay, the pair is M3 on the left and M20 on the right. So I'm going to try to maintain that geometry. I'm going to go put M3 over here, M20 over here, and then I'm going to try to get them overlapping. So I'm going to move that. There we go, almost. And then move that over one. And when they're exactly overlapping, then those white dots, which are the DRC errors, disappear.
What key were you using then to move it around?
I was using the keypad. So I've mapped the movements directions to the directions on the keypads. So there's your arrow keys on the keypad that does a screen pan. So I can pan right, pan left with the arrow keys. But if I go over to the
keyboard there, not keypad,
and use the arrow keys, then it's going to move the selection around right, left, up, down. And I think I can even do, northwest or southeast. Now there are other devices here. So this one is X5 and X54. I find those over here. Yeah, so this is also a pair. This is a current mirror pair. So this one is setting the current drive by connecting its source to gate, and then that drives another gate. So the one on the other side is the mirror that should be drawing the same amount of current. But because they're a current mirror, then they work best when those devices are also matched. I am going to, again, well, okay, let me start off with this. I have 54 on the left, so I'm going to leave it in the same arrangement as it is in the schematic. I'm going to move this over here and zoom in and match it up until the DRC errors go away. Okay, I've got two devices with differential pairs. Since in the layout, I'm going to keep this arrangement too, with the differential pair for the inputs over on the left side and the output drivers on the right side. So I'm going to swap these, take these two and move them over here, and take these two and move them over here. And now I can see these DRC errors. If I want to know, I know exactly what the DRC error is. It's a spacing between in-well, but if I wanted to know that, I can ask DRC why, and it says my in-well spacing is less than 1.27 microns. I'm just going to make sure that these things are far enough apart that they don't form a DRC error. So it looks like I need to move it about that far. Now, another thing I'm going to do that helps, I'm not sure if you're going to be able to see this at this resolution, but if I go to options and click on crosshair, then I get a little yellow crosshair that's very good for lining up things horizontally and vertically. All right, so I got that done. Now one thing I see is that I've got these long devices here. Let's see, which one is this one? This is XM4. XM4 is, that's the current supply going into my differential pair. So it should be close to the differential pair. It is about as long as the other devices are wide. If I don't care that much that the current is flowing the same direction, I'm going to just rotate this one. So rotate 90 and put it upright and then move it over here. And how close can I get it before it there? That's a DRC error. So move it a little bit back and about there. At this point, it gets to be mostly more of the same until I start doing the routing.
Yeah, I was
Don't
thinking.
know if you want to skip ahead and maybe answer a couple questions here. Some people ask you about doing fingers rather than having each device individual.
Mhm.
Yeah, you can do fingers. In general, what I'm going to be doing, I'll say this when I'm doing the routing, but you often get better matching if your current is always going in the same direction. If you do fingered devices, your current's going to be going in opposite directions. And yeah, you can do common centroid. You can do lots of things. You don't even have to use the P cells. You can flatten them. You can even edit the P cells themselves as long as you don't redraw them by hitting the apply button over there in the corner of the window. Then it won't redraw it. So there are multiple options there.
And we've got a question from Eric saying, is there any grid? Are there any grid alignment requirements for things like pins?
Yeah, Harold Brettel made a comment, why don't we have better alignment options in Magic? And yeah, we should. Yes, I could do it on a grid. Most likely, all these shapes are going to be at various sizes and pitches, and there isn't going to be a single grid that's going to work well to align those guard rings overlapping exactly, which is what I'm trying to do in the placement.
Mm-hmm.
And yes, I should have better options for alignment. My lack of alignment options sort of goes back to some bad experiences I had with commercial tools. Maybe they're better at it now, but at least back when I was doing it, their way of aligning things was very painful and usually wrong.
And we've got another question about what are fingers?
A fingered device would be when the two devices, instead of being in separate guard rings, they would be sharing a source or sharing a drain. Generally, that's considered the source where it's sharing. But yeah, and you could, that's an option. You can have number of fingers. If you look up in the window at the top, it says one of the options are how many fingers you have. It will do fingers lengthwise, so each device is sharing sources. And then if you put m equals more than one, then it will stack them vertically. So you can get an m by n array of devices, which I won't be doing here because there are too few devices.
Yeah.
Yeah.
I want to start playing the video again because I'm really aware about our lack of time.
Yep.
But maybe there's a question from Kennedy Casely about analog design using how does the P-cell stuff work, and also about floor planning from Mohammed Zakir. So I was wondering if you could answer them in text.
I don't seem to be able to
In the webinar.
text to everyone. Can you enable that for me?
Oh, right. There's a little drop-down button that says to, and then you can choose hosts and panelists.
If I choose host and panelists, that goes to everyone?
Yeah.
Oh, okay. All right, got it.
Cool.
All right, go play. I will.
Yeah. I'll start it from the routing.
Okay, so now I need to start wiring things up. So one thing I want to do is make sure I've got a nice big ground plane. So I'm going to start off with the local interconnect. Now, remember what I said about it acting like a painting program, is that if I want to, now I want to do essentially a flood fill of this rectangle with local interconnect. So I've got over here my icon bar, this blue. If you see up at the top here, when I put my mouse over the blue, it says local I. So the middle mouse button is like a pick function. It will pick this color and then paint it into the box. So all I need to do is put my mouse right here and click the middle mouse button, and I've got local interconnect. Then line up here. I want to do the same thing for the top. And that looks good. So again, paint like that. And I can do the same thing if I want to, if I want to put more down here, I don't have to go down over to the icon bar every time. I just need to find some place on the layout that has the same kind of layer and click the middle mouse button, and it will pick that layer and paint it into the box. I'm just going to do this everywhere here and make sure that I've got huge amounts of local interconnect everywhere. This is exactly the sort of thing you don't do for digital layouts, but it's very helpful for an analog layout to make sure that you've got as much ground and power plane as you can get over your entire circuit, because that's going to keep the resistance of the power and ground planes down. So basically, I'm tying all of these guard rings together with just a lot of local interconnect. Now, local interconnect is not a very resistive, or sorry, it is a very highly resistive material, which means that it is not especially, it's not especially conductive. So it's not a good thing for wiring, which is why I am basically trying to make it as big an area as possible. Also, you see how I'm painting. I'm not creating objects for this. I am actually painting little areas of local interconnect all around my design. The one thing that really highlights how this is different from the object-based thing is that I can just cut a hole in this. The same way with picking, I can pick an area of background in order to paint an area of background. So if I go over here and click the middle mouse button, I just erased a little hole in my drawing, which is something that's really hard to do in programs that are object-based. They don't like creating holes and things like that. Okay, so now we're making progress. One thing to note, as I said,
do you hit save, or do you find Magic to not crash very often?
It depends on what I'm doing. For basic layout, no, it doesn't crash very often. If you really want to save, there is a file, save. Here we go. And it would say 0 op amp write. I can write it. And then each of these is a subcell, so it's going to ask to write everything. So I'm just going to say auto write, which says, okay, I'm going to write every single thing. So now it's saved all of the devices. So yeah, I would recommend that. If you don't trust the tool, think it might crash on you, then don't hesitate.
I don't trust any tools.
No, you shouldn't. No, absolutely.
Okay, I'm going to jump ahead a little bit to the part where we're checking how, with using Magic, how you can check the connections. And Tim, the thing that I said earlier about the messages, it has to be set to everyone. At the moment, you're sending just a host.
Yes, I was trying to tell you that I don't have that option.
Okay, yeah.
But that works. You are copying my
I'm
messages.
copying and pasting.
Yeah.
So for now, so.
Yeah, if that works for you, then we'll continue with that. Now, at any point, it's very important to know what's connected up to what. That's very easy to do in Magic to find out what is connected to what. You can select a chunk, a region, or a net, which it defines in different ways, by clicking on the S key. So if I click on the S key once, it finds some tile area that is right under what I selected. And if I select it twice, it will select a little bit larger area that goes up to any contacts that are connected to that region. And if I click on it a third time, it'll show everything that is connected to that metal. So now I know that in that region that I just painted, it's connected to all of, I can see it's from the highlights, that it's connected to all of these guard rings, and it's connected to the contact I made along the bottom and all this area of local interconnect. Likewise, over here, it's connected to all of the guard rings. So I've got a well-connected now power supply, connects all the guard rings. So that connects all the in wells and all the substrates under the PFETs, and all the substrate under the infets are all connected together. So that's our starting point. Oh, by the way, all infets you want to connect somewhere to substrate, all PFETs you want to connect somewhere to well. And for those you need contacts. That's the point of a guard ring, is that it makes those connections. Otherwise, I would have to draw them by hand. But since part of my parameterized device is that it is adding the guard ring but itself, then that's how it's contacting. That's how I'm getting the contact from power supply to the well or to the substrate here. Just for the heck of it, I'm going to cut the via back from there. Now I've got some of my labels on my pins. So I've got a VCC pin. I'm going to move that here. Now I've got VCC connected here, VSS. I'm going to move down there. All right, so I've got 2 pins now that are connected. And if I select the net, it is highlighting the name VSS there and the name VCC here. So let's start wiring this thing up. And I'm going to start. First, let me give a little idea of how I generally wire things like this up, which is that it is helpful for things that have to connect across between a number of transistors, pop on up all the way to metal 3. So you don't want to spend much time on local interconnect because it's high resistance. So like for these device sources and drains, they're already immediately popped up to metal 1, but that means metal 1 is taking up the whole area here. So it's hard to connect things together with metal 1 without snaking it around everywhere. So it's easiest to connect things together on metal 2. So if you work out where the signals are coming in and going, you should be able to figure where you need to put metal 2 and how many of those stripes you need. The other thing you need to pay attention to is how big your transistors are. Figure out how much current is going to be taken up, and try to make the buses that are going to be connecting these things together as wide enough to carry that current, because you don't want electromigration issues. Now, if I were doing this for real for a product, I would go look up the electromigration rules. I would figure out exactly how big I need to make this thing, so as not to overdo it, because if I make it too big, I'm just adding capacitance to it, which is not necessarily good for the circuit operation. So I want to keep it, the wire small enough, but large enough to meet electromigration rules. And as I said, I'm not going to spend the time to look that up, but those are the kinds of fine-tuning things that you would do once you've finished a basic layout and have it LVS and DRC clean. Then you can go simulate and look up electromigration rules and then fine-tune things. So back to wiring. Let's start with the inputs. We got minus and plus inputs. Since I'm not going to be able to get metal 1 routing across here, metal 1 is actually pretty good for strapping the gate on both sides. So I'm leaving this contact, which is an option in the parameterized device, to have a poly contact both top and bottom. So I'm going to leave that there and then just connect it together with metal 1. And same thing over here. And I don't want to do that to here because these transistors are rotated. So the poly is actually going across, and it's the length of the transistor that's top to bottom. I'll come back to those in a minute. I need those inputs. This is minus on the left and plus on the right. So what I'm going to do here is I'm going to contact up to metal 3, and that seems useful. All right, I'm going to do it that way. There is sometimes drawing contacts can be kind of complicated, so I did put in my devices a way to draw extra devices. So if I want to draw a via 1, which would go from metal 1 to metal 2, then I'll click on via 1, and it tells me that I haven't made enough room for it. So there we go. Must be 26. So if I type box, I am now at 0.28. That's good enough. I'll call that good. And where was I? Go back to via 1. There we go. And it just painted my contact for me. I've got, I should always be looking at the DRCs. I didn't notice any DRCs there when it created. I've got 12 DRCs somewhere I've got to look up. But right now I'm just going to go ahead and do that again, via 1, and bring out my pins on top. So I'm going to paint metal 2 up there. And what did I say? Plus is on, no, minus.
Just going to pause the video there. Tim, do you want to see if you can answer in the Q&A section?
Yeah, I can answer. Yes, I can answer in the Q&A section. However, there are now like lots and lots of Q&A entries. So I'll work through them as I can. Yes, for lack of time, probably you should go ahead and move on forward and tell people they could watch the full video later.
I don't know why, but Tim can't reply to anyone in the webinar chat. So if you've got questions, then use the Q&A panel instead, okay? And then Tim will be able to answer there. So there's like a few recent questions from Saul and Harold and Zhao Chen. If you could put your questions in the Q&A section. Okay, so let me move on then. So let's have a look at alter. This is something that I learned from watching you, is that after you've made a transistor, you can then alter it. And with Magic, I thought after you placed it, you couldn't do that. So let's take a look at that.
Such a tiny gate, I don't need to strap it across. It's not like this is a important analog gate that I want to make sure that the electric field is constant across the thing. So I'm going to go over here and I'm going to find the thing that puts the contact at the bottom of the gate, where it says add bottom gate contact. I'm going to clear that and type apply, and that just disappeared, that contact. And since that caused the whole device to shrink a little bit, I'm going to have to go contact that back in again and add some more. Come on, back there. Add some more local interconnect on top. All right, now I've got that little switch over here. That is gated by enable N. I've got to get that enable N through somewhere. Let's go ahead and just connect that in from the beginning. So that was going into M4, which was this one, right? Yeah, so that enable N is gating this, which means it's going into here. So let's put, again, a metal 2 strap across here. and contact that here with bio1. Just going to go ahead and contact both sides and enable in. I'm going to move here. I'm going to do the same thing that I did before, which is to set label layer metal 2.
More of the same. Shall we jump ahead?
Metal 2 and then erase metal 1. So now I've got my enable in line on metal 2 that gates into here and ultimately needs to come down here and get this.
Should we jump ahead then? How about finding DRC errors? That's handy.
My DRC error is, I'm going to say DRC find, and then I zoom in on that and it says, oh, here's my error. That's pretty simple. Just hover over that slot and that's the last of my errors. All right. So we got the bias done. The bias goes into this transistor. That's all done. It's all gated. This goes into here. Have I missed anything? That might be everything. Let's see, this one, this one, this one, this one.
It's at this point that you really want, so would it be so helpful if you have air wires, like when you're doing a PCB and you know where you need to go to connect what?
Yeah, we call them fly wires.
Fly wires.
Over here in America. I haven't heard that term before. You said air wires.
Yeah.
Okay, I'll have to remember that term.
I think I learned that from KiCad. Because when you're doing a PCB, you do the schematic and then you have the layout and you just can see where everything needs to route. It takes that mental load off. Okay, and now let's jump ahead to doing the extraction. So that the layout is nearly done, and what needs to happen next is you've got to extract the circuit from it so we can run the layout versus schematic to check that it matches the schematic. It was pretty quick.
And so from here, I would just need to do LVS. So I'm going to do write all, which is how I save everything. And then I'm going to do this, which is extract, extract do local. I don't think I need that option, but extract all, and then say X to spice LVS and X to spice. And I think that was actually a stupid thing to do. I think I just wrote over doesn't matter. Yeah, so I just wrote over the one that, no, actually the one that that Xscheme made was saved to the Xscheme directory. But let me do this. I'm going to move 0 op-amp.spice to 0 op-amp layout.spice, and then I'm going to copy the one from the Xscheme to here, and then I can run netgen on it. So I'll say netgen dash.
Oh, you got net get there.
Sorry,
you got.
Yep, thank you for that. Dash batch LVS. Then I give it the name of the two layouts. So I want layout, which means I want my layout one first, and then I need to give it the name of the cell itself, which is 0 op-amp, and then the name of the other one, which is 0 op-amp .spice and 0 op-amp, and then I need to give it the name of the setup file, which is user share pdk sky130a libs.tech netgen sky130a setup.tickle. And then of course it tells me it hasn't matched because of course, if I'm doing something this fast and paying as little attention to it as I can when I'm talking at the same time as I'm doing layout, then of course there are errors. But that's what I wanted anyway, because I want to give some instruction on how to look at the netlist LVS layout and see. So by default, it creates a file called comp.out. So if I look at comp.out, I'm going to see some output that I don't care much about. It's going to be comparing devices that I know are already equivalent. And this is interesting because you see it says removing 0 valued device. So because the schematic has these little, you see these little arrows in
Mhm.
here. So these are voltage sources, 0-volt voltage sources that it puts in for current measurements. And so they end up in the net list, but NetGen is clever enough to notice that these are not physical devices because there's no way to make a voltage source in layout. So it simply says, oh, look, it's a 0-volt voltage source. That must be part of the schematic for current measurement, and it removes it. Likewise, actually, I should say not likewise, but contrariwise, it has taken these little capacitors here, which are representing parasitic capacitance,
Yeah.
and it added them in. So
Yeah, I can
that's
see
my
that, yeah.
that is my main problem right now, is that my schematic netlist has these devices C, and my layout doesn't. Now, I don't know if there's a way in NetGen to, a way in XGame to extract the circuit without the parasitic. So I'm going to take the hack solution and just look at my 0opamp.spice file, find the all the lines that begin with C and delete them.
I'm going to interrupt your hack here, Tim.
Sure.
And then what happened was then when we overwrote the spice, we lost that hack. So I'm going to just jump ahead to when we got the correct number of devices, but the net didn't match.
Yep, I've got 14 nets. So I've obviously failed to connect something or split something up. And here, this is pretty easy to see. You see, I've got a number more nets over here than I do on that, but all the individual entries, I think, add up. So my problem is that over here, I've got net G1. It's net G1 is connected to the source or drain, which is pin 1 or 3 of 2 devices, 2 InFET devices, source or drain of 2 PFET devices, and the gate, I guess, of 2 devices. So if I go over here in my schematic, G1 is connected to this gate, it is connected to this gate, and it's connected to the source drain. I don't remember making this connection. I bet this is, oh, that's right. I remember connecting these 2 together, but I did not connect them to anything else. Yeah, there we go. So that was this line over here, which is the source and drain of these devices. So that should have been,
because it's unconnected, it counts as a separate extra net.
That's right. So I see that over here as probably something like this.
Let's jump on to the bit where you labeled in Magic.
Going in M4 comes out to here. So this line over here, this is called SP in the schematic. So I can do this, which is go to text and give myself a little smaller text here, like 0.5 microns high. I'm going to call this SP. And I'm going to make sure it connects to the right metal there. We say metal 3 and apply. All right, now I've got a label called SP. Now that one went through minus, and the other side of minus is the self-biased one and is G1. So this thing here is G1. So, whoops. G1, and then that makes the other side G2. Should have done that earlier on, so I know what I was. So did it? Oh, it already moved it. It saw there was that mistake that I made with metal 3 and it changed it. All right. Anything else I need to? Yeah. No, I think that's all the named nets in here. So that should help too, because in my LVS report, I'm getting these names here, like these are automatically generated names, and it says that there's a wire on metal 1 at this position, 5896, negative 1296. And I can use that generated name to track down where it is, but if I've labeled it, it's going to be a lot easier. So
yeah, so then we'll jump ahead to the last LVS error and see that.
I've connected up something wrong. I think that last connection must be wrong somehow. Yeah, so what is this? M1 5896 N1276 is This one. Yeah, it seems to be, how is that backwards? M54.
Okay, then let's jump ahead to.
There you go. You got me thinking over the problem in real time.
Yeah.
Did
So
I
that's
do
problem with-
my thing? Yes, now you see. Circuits match uniquely. Now, why does it say they're port errors?
And what we realized the port errors was due to you debugging using it like a version of NetGen that you were debugging at the time, right?
Oh, yep.
Okay. So then I think then the last bit which we can maybe just talk about is you've got your GDS, the LVS matches, and now you want to take your simulation, you want to run that in Xscheme to see how it compares with your original simulation to check that your layout matches well enough. And what would you recommend to do for
that? It needs to be set up correctly in Xscheme so that you can swap out. So if you have your subcircuit as a block that you can substitute in your test bench, the block that is the schematic with the block that is the netlist itself, then you can swap one for the other and do the simulation on that. That does require that you have the proper hierarchy, that the test bench should be separate from your schematic, which is the way it ought to be anyway.
Okay.
Yeah, it's a little hard to describe without going through it, but that's the general idea.
Yeah. A number of people have asked about can we get access to these the layout? So that would be good if you can put that in a little GitHub repository and push it, and then we can share that on when we send out the link to the recorded video. So
yeah, sure. Yeah, I'll do that.
Open this with Magic and see how that whole thing works. Great. Okay. So that's got to the end then of that recording. So we'll invite Thomas back onto the stage if he's still awake.
Yep, still here.
Hey, Thomas.
Hey.
Yeah, so I was just wondering, like, was there anything in there that was new for you? Like, given like what you've seen of the Magic layout, any comments or opinions?
No, not really. I haven't done a circuit that large in Magic, but it was good to see that from my side myself. So I just kind of jumped over the K layout straight away.
Yeah. So, and maybe you can just explain why you wanted to go with K layout.
Yeah, so it's about the kind of the user model and how you interact with the program, and K layout is much more similar to the kind of commercial tools like Cadence or Tanner. The way the user interacts with the tool is just much more similar and more natural. So it felt more natural from my previous experience to use K layout. That's the main reason.
Okay. So we'll play your video now. Actually, I'm going to launch. I've got one other poll to launch. I can share the results, I think, of the previous poll, and also launch the other one. There we go. So this is for you to tell us what other topics you'd like us to cover in future webinars. And while that's running, I will start the video playing. Of the recording that we did with Thomas. So let's just jump straight into here. And we didn't record the sound over this one, so we're just going to talk over it, Thomas. A number of people have asked also where you can get all these tools and get them all set up. So these are all the open source tools. And what we're using here now is Harold Prettel's Docker. I can share a link to that. And that made it very easy for us to get set up. And then when you start Magic, it is loaded automatically with the Sky 130 technology, all nice and automatically.
Yep. So maybe we should talk about the kind of the general approach here. So in Klayout, there are some P cells to generate the cells of the primitives, but they're not as well maintained or as advanced as the ones in Magic. So what we do here is we generate the devices in Magic, and then we export them as a GDS and then import them to Klayout. It is a bit of a laborious process, and as you mentioned earlier, it took about an hour to do. There are definitely ways to speed that up, starting with the Spice import, and you can probably integrate that into Klayout as well. There are P cells in Klayout that could be used. I just haven't used them myself, so I didn't use them for this demonstration.
One question I had for you after watching Tim do his layout was he used the guard ring and used that the contacts on the guard ring to contact the transistors, and that was something that you turned off when we generated all these transistors.
Yeah, so I noticed that as well. I mean, maybe that's somewhat of a personal style thing, but certainly any layouts I've seen or worked on have not used guard rings on each individual device. So basically the motivation there, I guess, is mainly that you're going to have a tighter, high density layout because you have more space. Probably more liable to have latch up. But yeah, I've always used it without individual guard rings. So that's kind of what the process I've used here.
Okay. And then I've got a like a section here where there we go, where we're speeding up. Because we basically do this for all the transistors, and then we had to name them all. And then when you import them into Klayout, you have to rename them.
Yeah, it's a pain. It's easily scriptable. I just haven't done it.
Yeah. What you've done quite a few scripts and things like that we'll be seeing later. And they're shared in the Klayout repository that was linked from that slideshow that I shared at the beginning. So if you want to access Thomas's resources there, you can get them from that link. Okay, so and then this is I actually was mentioning this to Harold Prettel today. It was on the Docker at the moment when you load Klayout. It's not quite as tightly integrated as Magic is at the moment. So when you start Klayout, it doesn't start with the default Sky 130 technology. So this is how we did it.
Yeah. That should be easily fixed. I think it's just installing it before the Docker's packaged up.
And the files in the right place, so Klayout knows where to find them. So you've got to find that LYT file and the tech directory, libs.tech for Klayout. Did we just paste it in the end?
Yeah, we basically import that file or that maybe the directory, and it picks up the files. I can't remember exactly.
There we go. There's a lot of us scratching our heads in silence.
Yeah.
Oh, I remember what it was now. It was there we go. It was right clicking on that left hand side and saying import technology, and then pasting the link.
Okay, yeah, and then we started the layout here.
Yeah, so now this is like after Klayout is set up.
Got all the layers on the right hand side, which is nice.
So let's jump ahead to when we're making the arrays of that first transistor.
Mm-hmm. So here we've basically went to File, Import GDS, and we've imported the GDS that we exported from Magic to get that cell in Klayout. And then there's also some defaults that maybe aren't ideal in Klayout. Things like shallow copy and shallow move, which allows you to, well, by default, it's deep move and deep copy, which means you can go into side cells and move things around, which is probably not what most people want to do. So we made some changes there to the defaults.
And what was the reason for changing the cell origins?
I think it's just because when they exported, the devices weren't on the origin was kind of a weird place, which means that, I mean, it's maybe not 100% necessary, but it's good practice to have your origins in a good place, the bottom left-hand corner. And here we basically make an array. So rather than copying the device, we kind of use this array instance to allow us to make multiple devices. In this case, just two. Oh, yeah. So I'm guessing this is the input of the differential pair.
Yeah, so let's jump ahead to one of the drawing modes, the partial mode.
Mm-hmm. Yeah.
So, because it's much more point and click, and this partial mode lets you kind of just extend out the sides.
Yeah, so any shape has kind of vertices, and then you can drag those vertices around as you want. So in this case, I was inflicting my desire to have things lined up on you and making everything line up there.
Yeah, it was like, can we just splash it around like paint on a wall? And you were like, no, everything's got to be dotted and crossed properly.
Yeah.
And then let's take a look at the bit where we were. If you press F3, you get the editor options down here, and a really useful one is snapping to other objects and also making the angle constraints. Do you want to talk a bit about that?
Yeah, so snapping to objects is kind of self-explanatory. That means that when you move close to an object, it will snap to it. And then by default, you can move things in any angle. So you have freedom to, move in any angle. But for some, if you're copying things, moving things around, sometimes it's easier to make it either like Manhattan, I think it's called, which is where you basically lock it to certain angles. And then when you copy things and move things, they kind of stay aligned. So that's basically what we're doing there.
Yeah, you can see that's locked to kind of the 8 compass points. There we go. Okay, so now Klayout does do a bit of aligning. So let's see how you do that.
You can see here the bug that we encountered where the layer layers seemed to change how they looked with each operation, which is when we press Sky 130 at the top to basically re-import the layout.
Yeah, I don't know why that was happening.
Yeah, it's a bit strange.
It's one of these questions I'm reading now. Mickey's saying, oh, that was maybe a while ago, 656. Yeah, that was related to Magic. So S, when you press S in Magic, it just is showing connectivity. It doesn't know what's meant to be connected. That's like, in my mind, one of the things that makes doing this quite hard, because you have to, in your mind, like know what you're doing. You don't get the air wires or the fly wires.
Yeah, you have to hold a lot in your mind. It gets easier the more you do it, but yeah, it's not quite as convenient as PCB when you just have to kind of connect between the two highlighted points.
Okay, let's jump on to seeing how you do DRC then.
So here there's two approaches. You can export to GDS, but you can also do it inside of Klayout. So I think that's what we do here.
Do we have a problem here? We had to like import it somehow.
Yeah, I think so.
There was at this location again. So this is another thing that can definitely get sorted out by having the Klayout stuff set up in the Docker that we were using.
Yeah.
Paste that in there. And then we got these projects here for running the DRC, which is just basically, is it Python or is it Ruby?
I think it's Ruby, the DRC. So okay. Klayout now has support for Python, but it started with Ruby, and some things like I think DRC and LVS have to be Ruby.
Yeah. Okay. So that's that's running the DRC. One thing that's nice with Magic is that it's kind of running the DRC as you go. So if you make a mistake, it immediately highlights it for you.
Yeah, that is nice. Yeah, it would be nice to have that, but I think it's even kind of commercial tools. There's some online DRCs, but kind of the default, if you're using something like Virtuoso and Calibre, is you still have to go through this export. Not export, but you have to kind of click things to make it run.
One question we've got in the Q&A is why do the layers in the PDK have the two numbers like 64-20?
So that's the GDS numbers. So Klayout is actually kind of unique in that you're not even operating on an internal database, you're just really operating on the GDS. And the GDS, the file format that's kind of standardized to communicate the layouts. And within that, they have these kind of structure where you have a data layer and a data type, I think. But basically, for example, the NWEL drawing is the NWEL is 64, and then the 20 is saying it's a drawing, opposed to, let's say, text or some other function. Yeah.
Right. Okay, so yeah, sped this bit up. Let's see, what else should we talk about? Let's jump to your Klayout repo.
Okay, yeah.
Klayout setup.
So in here, there's trying to use the wrong shortcut keys when I was used it as a small piece cell library.
Yeah, so it's the shortcut keys to make it match with Cadence and the P cell. So we can jump to where you do the setup of the keys. Setup. And that's where you can get all the shortcut keys done. And then let's take a look at the P cell, because like we saw with Tim doing the magic one, you can make that or like a parametric cell just from the top menu.
Yeah.
And what you did, you've written a little Python script, is it? There we go. This one.
Yeah, it's a Python. I'm not sure you call it a script. Well, I guess it is. But yeah, a little bit of Python that will basically generate contacts. So it means you just speeds you up a little bit.
Yeah. So you just set the bottom layer, and then it will do the contact between that and the next one, right?
Yeah, exactly. And you can set different number of contacts in X and Y plane. So this is how a P cell would work in Klayout. I mean, it is a P cell. So, for example, the MA brains P cells, which supposedly have transistors and more devices, would also use this.
I'm not hearing your audio so great right now. Or video. You're frozen. All right, so let's jump ahead to drawing the N well. Are you back, Thomas?
His video is frozen.
Yeah. No, I have to pretend that I know what I'm doing with Klayout. Are you back, Thomas? I just got a one frame update.
Can you hear me? I can hear you. Okay, good.
I just jumped onto the drawing that the N well.
Okay. Yep.
Interesting how you did the N well and all the PMOS on the left, and then we've got the NMOS on the right, and Tim did it top and bottom. I guess that's just a stylistic thing, is it?
Yeah, I mean, we didn't really like floor plan as such before we started, so it just kind of evolved. It is interesting. I wonder if you rotate ours 90 degrees, how similar it would be, because they both have the same like aspect ratio, just in a different direction.
Okay. Let's jump ahead to using the path tool. That was cool. So it's a bit like the wire tool in Magic. You can set the width. I do like the kind of the snapping that it does.
Yes, it's quite useful. It just makes things a bit easier if you want to make things line up.
I think the first part of the layout I was doing it, and then we changed over to you now. That's why it's a bit faster.
Okay, yeah.
I
think about halfway through we realized it was going to take a very long time, and then tried to speed things up.
Hong Hai Tai says, have you tried importing GF180 into Klayout yet, Thomas?
I mean, I've installed the PDK, shall we say. And yeah, I haven't tried to design anything with it, but I know that the PDK installs. I think the default colors weren't amazing. I think you actually had a slightly better version of the colors for that. But yeah.
And hi Maximo, is saying, do you recommend running the final DRC in Magic, or is it enough with the check from Klayout?
So when I was doing it, I did it in both Magic and Klayout and kind of checked it twice. So I would probably say that as a default. Because yeah, there might be things that aren't caught by one or the other, and it's better to have that. It's kind of up to you how quickly or how often you want to do that. But I would say it doesn't hurt. So it's probably good practice to just double check with both.
I know that the default in Open Lane is to run them both.
Yeah, I mean, I think it has almost no cost, so it's just to do it, and it helps prevent any pain down the line.
Yeah. Now we're getting kind of close to the end of the layout here.
Mm-hmm.
Again, it's crazy to me that you can kind of remember what all the MOSFETs are and which ones are meant to connect to what.
I've worked with some people that have made circuits like maybe 10 times more complicated, and just do it all in one go and then press LVS and it's correct. It's
wow.
Yeah, I guess you just learn.
So do the kind of proprietary tools not have the air wires as well then?
So talking about cadence, I mean, there's different versions. So they have like Layout L and Layout XL, and I think Layout XL does have some wires, some more schematic driven layout. I've predominantly used just Layout L, which is slightly less fully featured, and I'd say that's basically not that much more advanced than Klayout. There's a couple of features, but the Layout L is kind of on par with Klayout, I would say. And then there are some more advanced features with the XL. Yeah.
Now we're in turbo mode for layout. Vishesh Jain is asking how I'm going to share the link shown at the beginning. I'll paste them again in the chat. Okay, and then let's jump ahead to when we finish the layout. So that was the final bit. There we go. And then loading it into Magic. So then to do the LVS, we then go back to the same Magic flow that you saw before when we looked at Tim's flow. So that's how it looks like. First off, that's how it looks like when we loaded it into Magic, and then the rest of the flow is the same. So extract, and then run NetGen, and then go back to Klayout to fix your issues.
I would say that Klayout is capable of doing LVS.
Yes, already, or it will be.
I mean, it is in the sense that the engine exists and it can be used. It's just, as far as I'm aware, no one's made the LVS rule set for Skyward 13.
Okay. Okay, so where are we at then? So we've got 4 or 5 minutes before the schedule is over. So maybe I'll just invite Tim back on to say hi, and we can do one last round of question answering.
Yep, I'm still trying to answer questions in the chat or the Q&A, and where'd my video go? And it's there's still more questions that I can answer. So if I missed, I'm trying to answer everybody's, but if I miss something, then I'm sorry.
I will also take the opportunity to post the link to join the Slack and the Google Doc I had earlier. So yes, that's if you want to keep on asking questions and get more involved, we have an analog channel in the open source Silicon Slack. So that's probably a good place to go. Tim, I want to ask you the same question I asked to Thomas, like after seeing the K layout flow, is there any features that you're kind of jealous of? Do you have any comments on that?
My opinion of K layout is that there has been a need for a modern layout tool for a very, very long time, and K layout is getting there. There's still a lot of development work to do. I'm happy to see development work in K layout. I'm happy to see people use K layout. I of course have my preferences and my long history with Magic. It's probably always going to be my preferred tool, but the different tools have different styles. I think if you have open source tools at all, it's better to have multiple open source tools, and it's better when the multiple open source tools approach things in different ways and not one size fits all always. Yeah, there's always things you look at and say, oh, yeah, I should do that. And if you have the time, you'll go put that in or not, depending on how complicated it is.
Yeah, and we've seen both the tools improve quite a lot over the last year or so, I'd say.
The open source PDK has been a huge driver, I think, for both tools, is that there are more people using them. And so the more people use them, the more they find things that don't work or things that they want implemented. And there's a lot of pressure to keep developing. That also keeps them fairly unstable, but that's a separate problem. Yeah, lots of development, lots of work. Also, each time you do a new process, you find things that are specific to that process that don't work with the tools or break the tools, and then you have to play catch up a bit to get it to work with that process.
How do you think about some kind of standardized PDK? Do you think that'll ever happen?
Standardized PDK? Well, there used to be a standardized PDK called SCMOS. It broke. The problem with the SCMOS was that it only really worked for down to about 0.5 microns and below, or maybe 0.35 microns, and below that it kind of fell apart. There is a thought that the FinFET devices, because they are so restrictive, actually make it easier to standardize. But until the FinFET processes are so old that foundries don't consider them their golden egg, then they're probably not going to open source any of that stuff, and that makes it very hard for us to integrate the rules for FinFETs and things like that into open source tools. It'll come along eventually.
Yeah.
Okay, so now's a good time to wrap up. I think we're just right on the 7:30 my time. So just like to say thanks again on behalf of everyone for Thomas and Tim. We really appreciate your expertise and giving up your time to come along and answer all these questions and show your process. I think one of the reasons why the webinar was so popular is because there's very little out there in the way of learning how to do analog stuff. So great to get an insight into your methodology. Please say thanks and put a thumbs up in the chat if you enjoyed the webinar, and look forward to seeing you all on the next one. And don't worry, this has been recorded and it will go up on the eFabless YouTube channel with some slight editing probably. So yeah, thanks again, and have a great rest of your day, and have a good weekend.